Dr. Sparrett. I'm the director of the Biocomplexity Institute, and I want to welcome you all to this happy event. I'm privileged and excited to welcome Richard Stearns and Daniel Rosenkrantz to be our first speakers in this series that I hope you'll attend with us. It's hard to really explain these two people from the point of view of me and from the point of view of the Institute, but they've been absolutely instrumental in the small world of our own work here. They've been absolutely instrumental in helping us focus and frame our theoretical program over 20 years or so. It's just been an incredible privilege to have them associated with us and to see how clearly they perceive the nut of the problem oftentimes that we're confronted with. It's remarkable. I want to say one personal thing about it is that when I was in graduate school, there was a certain interest in making sure that we were rigorous in this program I was in, which was essentially a neuroscience program. It was a little different than that, but what we would call now probably neuroscience. And one of my mentors had been a student of Tarski. And the long and short of it is that he told me that if we were going to have anything to talk about, it was going to be formal and it was going to be important, then we were going to frame it on the concept of formal languages and how they relate to both logic and computation, compilers, and the relationship of tractability results to practical problems. And what he told me to read was work from these two men. So that was a long time ago, and I never really told him that before, but it's a remarkable thing to be introducing them at all. So thank you very much, Dick and Dan, for everything for so long, and welcome to the Biocomplexity Institute. I don't know if Kevin is here yet. Is Kevin here, Grace?
Yes, Kevin is here and should.
And I'll hand this off to the computer science department head, Kevin Scadron.
Great.
Anyway, welcome.
Go ahead, Kevin.
Well, it's really a pleasure to welcome everyone and to welcome Dan. Dan, as Chris was just outlining, is a giant in the field of computer science with a long career and an incredibly long list of contributions. He got his PhD in electrical engineering in 1967. So for those of us here, that's roughly contemporaneous with when Bill Wolf got his PhD. And Dan then spent 10 years at GE's R&D Center before joining the faculty at SUNY Albany, where he spent most of his subsequent career, aside from 2 years as principal computer scientist at Phoenix Data Systems. His time at Albany includes a lengthy stint as department chair, which of course resonates with me and all that goes with that. After retiring from Albany, he began collaborating with the Biocomplexity Institute, first at Virginia Tech and now here. And Dan has been recognized as a fellow of the ACM and also received the ACM SIGMOD Contributions Award in recognition of his contributions to the area of database systems. But it's really important to note that his contributions span so many areas of CS, not just database systems. You know, he really is one of the pioneers in the field. And so his contributions span not only databases, but theory, compilers, languages, VLSI, and I could go on for quite a bit more. So we're really lucky to have Dan speaking today, chatting with us, and to have him as part of UVA, as part of the Biocomplexity Institute and the Department of Computer Science. And so it's really my privilege to welcome Dan and to introduce him. And so I'll pass the baton now.
So thank you very much, Kevin and Chris, for a wonderful introduction. I'm Madhav Marathe, along with Professor Ravi and Professor Anil Vullikanti. I'll serve as a moderator for this session. I want to welcome everyone to this incredible session. And Kevin has already introduced Dan, so I won't go into the introduction again. Just to add to what Kevin said, Dan was also the editor-in-chief for JSCM, which is without a doubt the flagship journal for computer science for all these years. I want to start by just a small personal note, and then we'll get into the details of the meeting. But on a personal note, I would like to begin by saying that I'm immensely grateful to Dan for his teaching, guidance, mentorship, and support over the last 31 years. I joined Albany in 1989 as a graduate student and started to work with him right from the first semester. It's somewhat unusual in that usually a student gets to work with a professor and his group of other students during the course of their PhD. I was incredibly lucky that I had a chance to work with 4 absolutely top-notch professors, Dan Rosenkrantz, Richard Stearns, whom we'll hear from tomorrow, Professor Ravi, who is online today, and Professor Harry Hunt. It's really we're very lucky to have professors of this quality to be able to work. And my guess is we have written more than 75 articles during this 31 years. And even today, myself, Dick, Dan, and Ravi meet about every 2 weeks in the evening and talk about research and work on problems together. Dan's insight and ways of approaching a problem are absolutely unique. I have not seen many folks with such incredible problem-solving skills. And yet, I think most importantly, for all his achievements, Dan's humility and dedication to research is very inspiring to me. He's an absolutely humble person who is always reachable and always there to give advice. So Dan, my sincere gratitude to you for your mentorship for the last 31 years. So with that, let us begin. Our plan is to have a discussion till about 2:45. As you all know, we have opened up a few slots afterwards so that folks can talk to Dick and Dan, and have personal conversations with them. The plan is in this discussion is to have the discussion broken down into 5 parts. I will be the moderator for part 1. Ravi and Anil will be the moderators for parts 2 through 5. In each part, myself, Ravi, or Anil will ask a few questions to seed the conversation. And then after the discussion is done or Dan has answered the questions, we'll open the floor for folks to ask additional questions that pertain to that part. Our goal is to try and keep each part to about 15 minutes so that we can have a chance to touch on all parts and still finish on time. So with that, Dan, welcome again. And if you're ready, we can start now.
Well, thank you very much. I'm really very glad to be here. This is an exciting event for me, certainly. And I thank you for the kind remarks before this, but really appreciate it.
Thanks, Dan. I think words just don't do justice for all the things you've done for all of us. So my first question, of course, goes back to your early schooling days. So the question is, you did all your schooling in New York City. How did you develop an interest in science and engineering? And were you influenced in taking up computer science by your family and your teachers?
Okay. Well, I think I was always interested in math and science, particularly in high school. I realized that what I really enjoyed the most was math and also science, physics and chemistry. So I had that inclination. And also I was very more interested in the applications. Like engineering appealed to me because it was applications of math and science. So I had that orientation. And in college, I originally thought I'd be interested in chemical engineering, but then I realized that throughout my career, I kept getting more and more attracted to math, and particularly abstraction. And so chemical engineering didn't seem abstract enough to me. So I went to electrical engineering, and there was no computer science then. So I really liked electrical engineering and kind of thought that would be my field for life, actually, pretty much. But, actually did some circuit designs and things. And so I liked that. But then when I was a graduate student, at some point, I realized that I really liked the emerging field of computer science, even though it didn't exist yet. And originally, I thought I was interested in signal processing. But at some point, as a graduate student, I realized that discrete math appealed to me more than continuous math. And so I got interested in computer science, particularly what they call switching theory. And that's what I was originally interested in.
Thank you. So my next question is a nice follow-up on this. Can you briefly describe your graduate school experience? For example, we understand that Jeff Ullman, who is a very well-known computer scientist and a professor at Stanford, was also a student at Columbia at the same time. We also heard, and you can correct us, that your nickname in graduate school was Mr. Counterexample. How did you choose your research topic was the additional question I had.
Yes, well, Jeff Ullman was an undergraduate with me. I was actually in electrical engineering, and Jeff was in something like called applied math, something like that. We were there, but not necessarily doing the same thing. Then he left. Then he went to Princeton for his PhD. Again, as a graduate student, I soon realized I liked computer science and discrete math, and then within computer science, I liked switching theory, which was basically discrete math, and partly I like discrete math things in computer science because I enjoyed making counterexamples for some reason. And there's more opportunities for that in discrete math and continuous math, to me anyway.
That's wonderful. So the last question in this first part, and then we'll open it up for questions from others. I just want to let you know, Dan, that many of our students from Albany have joined. We had told them, and that's why I want to keep the time for them to ask questions. I'm sure they have many, many questions that they want to ask. So let me ask the last question for this part. What inspired your thesis work under the supervision of Dr. Steve Unger on formal languages? Your work in formal languages is remarkable, in my opinion. So if you could kindly describe the results briefly in your thesis, and more importantly, you did this work when I think
I started Steve Unger really working in switching, but he actually started doing something, actually algorithms for context-free grammars, sort of as my end in time as graduate student. But autonomous theory was emerging, and particularly, again, I had this applied inclination, and formal languages. Chomsky had written these very influential chapters in the Handbook of Psychology on formal languages. And compilers was excited to merging new technology, which seemed to be based on context-free grammars and formal languages. So it just attracted me, maybe because it was more abstract and kind of seemed very have a lot of potential for interesting problems. And my dissertation was on programmed grammars, which was really driven by the need for extending context-free languages. They were context-free grammars were a good vehicle for describing structure of things, but not certain compiler issues like symbol tables and identifiers and things. And context-sensitive grammars were used for that, but they were atrocious, very hard to use and write and understand, way too complicated. And so I was trying to develop an extension of context-free grammars, which would handle these things like identifiers in a way which is more natural and simpler. And actually, right at the same time, Alejo was coming up with his index grammars at Princeton, more or less addressing the same issue of coming up with a more intuitive, simpler mechanism for extending context-free grammars. So that's, that's what really enticed me into that field, or that topic, I should say.
Great. I'll just ask a quick question, then open it up. Did you interact with Alejo as well at Columbia or later on?
No, not at all. I met sort of the very last year. I was working on a dissertation. I spent a year at Bell Labs in some kind of position. I don't remember the title, the temporary position, to basically work on my dissertation. And Jeff Ullman and Alejo were both at Bell Labs. I think Alejo came while I was there. So I interacted with them at Bell Labs.
Great.
That's really where I had more interaction with them.
Okay. Great, Dan, thanks. So let's open the floor for questions so that others can ask. Paul, how should we go about doing this? People raise their hands. I think Grace tells me that person who wants to ask a question should unmute themselves and then ask the question. Is that correct, Grace?
Yes, people will be able to unmute themselves. So if you have a question, please unmute and go ahead and ask your question. And Madhav will field those.
Yes.
Or Dan will answer directly.
Yes, Dan can answer directly for most part.
Yeah.
Yes, thanks so much, Grace. So yeah, go ahead, please.
Hi, my name is Venkatesh. I'm also a student of Dan and Dick, and I also overlapped with Madhav for most of my PhD, and I was also a student of Professor Ravi. So you talked about grammars and other areas, but you also worked on databases, right?
Oh, yes.
So
yeah, I didn't really get interested in databases until I was a GE.
Okay. And what kind of work did you do in that?
You have the questions on databases in part 2 or 3. So if you want to hold on to those.
Yeah,
yeah.
Sure. I just wanted to know what.
Yeah, absolutely. That's a very good question.
Yeah.
I just thought that we will move chronologically.
Sure.
But go ahead. Finish.
Yeah, I just wanted to know what kind of work he had done and how he moved it along.
Yeah, absolutely. I think Venki has become one of the experts, Dan, in database at Oracle, and then now he's moved to other places. But Venki, if it's okay with you, we can hold on to that question just a little bit and then back.
Sure.
Okay.
Hi, Madhav. This is Parvati here. Hi, Dan. It is so nice to see you, Ravi. Hi. And John Stillman. Yeah. Hi, everyone. So, Professor Stearns, I'm incredibly fortunate to have had Dan as my advisor, PhD advisor, and I learned algorithms from Ravi and Professor Stearns, and it's so nice to see you all, and you have had tremendous influence on my life. So yeah, so I had a question for Dan about his whether he had a specific style when he was advising students, and whether he approached it, if he had any philosophy while advising us back in Albany. Thank you.
Okay, thanks, Parvati. Dan, please go ahead.
Okay, well, I'm not sure what the style was. I think I tried to get you and other graduate students to define some topics that you were interested in, and then sort of get you, in general, have you make some contributions. They'll start off solving something, get started to sort of get confidence that you can actually solve problems. And once you have that confidence, then you could tackle more difficult problems, more open problems, more new things. And also have a lot of conversations, have frequent conversations in front of the blackboard, just go over things
Right.
and then sort of get you launched to do your own thinking.
Right, right, right. We had such frequent conversations, and I learned so much from those conversations, Dan. Yep, thank you. Yep.
Thanks, Parvati. Take one last question for this session, and then I'll pass it on to Ravi for the next part. So any other questions anybody has for this part of the discussion?
Hi, Madhav, this is Ganesh. It's incredibly, I'm very incredibly happy to be here, to see Dan, to see Dr. Stearns and Ravi and you after a very, very long time, and all of you here. I have very fond memories of Albany, my initial discussions that I used to have with Ravi and Dan. All our theoretical formulations, and the way Dan used to ask me questions until I get the formalizations right. It's still very fresh in my mind. I had a question about Dan's early years. I still have fond memories of getting possession of a white book on compilers that was written by Dan Stearns while they were at GE still. In fact, if people had marketed it correctly, I think it would have been the very first compiler, on the market. All right, and that was and I still remember Dan's scores on compilers that it was probably one of the best courses I've ever attended. One question on that line is, why did some of those early work never see light of day as a product on the industrial market? And what prompted Dan to actually move from CRD to SUNY Albany? I mean, not that it was a bad move, because we all benefited from it, but then, I would like to understand that.
Great, thanks, Ganesh. Very good question. Dan, go ahead.
Okay, well, I think the products, actually, as a GE, GE was in the computer business when they went there. At some point, they sold the computer business to Honeywell, but they were actually had a big computer business, and this was our contribution. One of our contributions as a company was trying to encourage compiler technology, and our group, particularly Phil, Dick, and I, together with other people like John Hutchinson, were doing compiler work. And we were particularly interested in theoretical based framework for compiler generation. Our products we consider to be compilers. So actually, we thought the product could be compiler. We particularly me and Phil, get other people an Algol 60 compiler. We developed we pushed the theory, did more with top-down parsing and LL grammars, and really put a lot of focus what we call attributed translations, which was augmenting context-free grammars with attributes to handle things with like identifiers. And again, Knuth had kind of done that for semantics, but we focused on doing that for translations, extending syntax directed translation that way. And we thought of compilers as a systematic way, building a compiler to see how it went. And we built this Algol 60 compiler. The whole thing, every piece of it, and actually became a product. GE at the time had a essentially cloud computing business, which they called the time-sharing business. And actually, Don Shell worked for GE at the time. He was the head of the cloud computing business, the time-sharing business. Then he subsequently went to the R&D center for a little while at GE. So this was put on the product became a product of the time of that time-sharing business. And it was mainly used in Europe. In US, people mainly use Fortran, but it was also it was more widely used in Europe. And then Dick became involved in the Fortran compiler, which was developed by the GE computer business in Phoenix. He contributed to that. But we didn't think of syntax of compilers as a product. We thought of compilers themselves as the product.
Thanks, Dan. I'll pass it on to Ravi at this point so that we can continue to move to the other sections. So Ravi, want to take over the moderator role?
Yeah, sure, Madhav. Yeah, go ahead. I was hoping that the screen would be shared between me and Dan, just like it happened. Can people hear me? Dan, can you hear me?
Yes, I can hear you.
Right. Okay. Let me start. Please allow me to make a few personal remarks about Dan. I met Dan back in 1981 as a graduate student at the University of Pittsburgh. Dan was visiting to give a talk. I remember talking to him for about 15, 20 minutes on something that I was working on. At that time, I did not imagine that I would be a colleague of Dan and that I would get to work with him for 35 years or more. Okay. As many of his students and research colleagues would attest, Dan is like a magician when you talk to him about research and so on. Okay, he can see connections that many of us just did not see. I also think that he has a personal line of communication with God, okay, because during research conversations, he would say something like, suppose God tells us how to do this efficiently. Okay, if he says that, you can take it for granted that at that time, God has already told Dan how to do that. So again, it has been my great pleasure and privilege to work with Dan for the last 35 years. I'm just hoping that we'll continue to do for time to come, for a long time to come. Okay, I think I'm going to moderate two parts of this. The first part deals with Dan's work at GE R&D Center. Okay, the other part deals with Dan's work at SUNY Albany, okay, when I was a colleague of his. So let me start with the GE. Okay, some of these might be, maybe we can shorten some of these questions because some of these might have been asked already. Okay, so the first thing is, Dan, what was the GE R&D Center like when you joined? For example, did you spend time between research and applications? Okay, were you expected to work on applied problems?
I was the group, which was actually a very good group, which did both theory and applied work. I mean, the scope for theoretical work, obviously, that group with Joris and Dick had worked at foundations of computational complexity, which didn't seem to have any direct relation to ship to GE products. So it was a group which was okay to do fundamental research. But still, there was a view that whatever you did should have some impact on GE as a company. So again, I went there intending to work on compilers, which, because GE was the computer business, compilers complicated when the technology, the sort of custom that in those days was that you wanted to build a new compiler, you hired some people who had worked on previous compilers, and they tended to design it by taking each kind of statement, writing code to translate it, kind of simple versions, and then once they got that working, they extended, step by step, for more and more examples. So again, originally I thought it was compilers. Then GE got out of the computer business and was constantly exposed to different aspects of GE. But the group was doing both theory applications, and the philosophy of the R&D Center swung back and forth between how applied they wanted to be, have direct impacts on GE businesses, and how much they wanted to do fundamental research. I think all research labs have that swing back and forth. When they become too applied, they kind of get the feeling that they're missing out on fundamental work. If they think there's too much fundamental work, then they try to get people to be more applied. So it always tends to swing back and forth.
Okay, great. Some of these questions are going to be somewhat technical, so please excuse me for that. One of the results that Dan and Dick worked together early on was on table machine simulation. Okay, what is interesting about this work is that the running time was shown to be order n log n, okay, which is like between order n and order n log n. So this is one of the early problems which had an early natural problem that had a running time between order n and order n log n. So Dan, can you please comment on, how you came to work on that problem?
Oh, it was, again, motivated by compilers. Since we actually built these compilers, we did it for alcohol, which had this block structure. There was a problem with identifiers. You have all the references to some identifier like X, and then the declaration of these references to might occur later. With nested blocks, we accumulated these lists of references, and then suddenly a block would end, and we realized these things had to merge. And so we did this somehow or another, but we realized there was a theoretical problem of coming up with a good algorithm. There was kind of an obvious n log n algorithm, but we kind of, Dick and I in particular, had this feeling that there should be a better algorithm for this. And we tried to pose the problem more abstractly in terms of what we call table machines, and develop and present this algorithm.
Great. Okay. Dan, colleague Giri Tai from Albany wants to ask a question. So Giri, would you like to ask a question or comment? Giri?
Yeah.
Oh, great. Okay.
Just let me start the video. Hi, Dan.
Hi, Gary.
Nice to see you.
Good to see you.
First, let me thank Madhav and Ravi to organize this symposium, 3-day symposium. Not many people here may know, excepting Madhav and Ravi. I'm from SUNY Albany. I'm in the business school. And Ravi was my colleague at Pitt, not in the same school, but we were in different schools, but neighboring schools in Pitt. So when Ravi came to SUNY Albany, I was there, and we both were talking about things, but being in business school and Ravi being in computer science, we sort of did not want to get started anything till we got our tenures. And once we got our tenure, then we started to think about what work we could do. And obviously, the person with whom we would like to work and collaborate was Dan. It's very, very natural. What was amazing with Dan was I'm from a business school and I had a problem. And we started to talk about, this is about the dispersion problem of facilities. How do you put facilities where you maximize their minimum distance between those? And Dan was so amazing that he had more insight about the business problem than most business professors, which was really very, very amazing. That is when we started our collaboration, Ravi, myself, Dan. We worked on quite a few papers, though they were technical, but underlying all of them were business problems. And the results we got had a lot of intuition, a lot of insight, which was very useful for someone who is working in business arena. And once Dan left SUNY Albany, our stream of work kind of came to a halt. Ravi went off in his way, I went off in our, but we still fondly remember the kinds of contributions, insights Dan has made to us, both on a personal level as well as professional level. Dan had a very unique way of looking at bureaucracy. He used to make some very interesting comments about bureaucrats. His famous word for that was pencil pushers, was his famous word. So Dan is really an all-rounder. You may think he's just a compiler guy or a database guy, but he's a very good, astute reader of business situations, business problems. So I wanted to add that piece to Dan's portfolio there, because most of you would be talking about Dan's technical accomplishments, but he had so many other accomplishments. So thank you, Dan, for all the time, guidance, and mentorship, and the collaboration which you have done. It was a great, great learning experience, which is still very, very solid and is yielding a lot of results the way you think. I have tried to mimic it at least a little bit, not fully, obviously, I'm not capable, but that's been a great contribution you have made to me and, of course, to computer science and the general technical world. Thank you, Dan.
Thank you.
Thanks, Ravi.
Actually, Gary, I don't know if people know, but you have an OR background.
Yeah,
That means that one consequence, that was very easy to talk to you because you were stating things precisely.
Yeah, right.
And mathematically. So communications between us was very easy.
Yeah. Okay. Thanks, Dan. Thanks for your kindness. Thanks, Ravi. Thanks, Madhav.
Thanks, Giri. Yeah, Ravi, go ahead, please. Yeah, thanks, Giri. Thank you very much.
Yeah.
Sure. So yes, Giri and I did see Dan pull, rabbits out of thin air when we were talking about research problems. So that's great. Thanks, Giri. Dan, the next question is about your compiler book. I know Ganesh asked a little bit of it. Okay, let me ask from a different side. I had the pleasure of teaching the undergraduate compilers class based on this book at Albany several times. One of the interesting things about the book is that words like proof, lemma, theorem are not used at all in the book. I wanted to ask Dan, did it make it more difficult for you to write the book? And also, can you tell us something about what other books existed at that time? David Grease, I recall, had a book probably slightly earlier than you.
Well, there were some compiler books out before ours. I think the most influential was a book by David Grease, which really dealt with all aspects of compilers. It was also in the early 70s, Aho and Ullman had their books which focused more on parsing per se, and those were very good books. The books that Phil, Dick, and I wrote we wanted to make it very specific to what you need to do to build a compiler, because we involved in these two compilers for Algol and Fortran, Algol 16 Fortran, and we had this particular mechanism with attributed translations, which we thought could handle the entire syntax-directed aspects of translation, and so we wanted to highlight our technology, but not just us. What you saw of a complete technology for generating compilers, and we chose to illustrate it with a tiny little example of what's called mini basic, just to have, a running example. And with the style that both Phil and I had come from electrical engineering, and we've seen the style where things were not done as theorems, or there was really design theory. We called the book design theory. We've seen design theory for circuits and networks and control systems and other things, and that was our model. It's not mathematics, it's how to go about designing things, with examples and general techniques. And that's why we wrote the book in that style.
Great, Dan. The next question is about the traveling salesman problem, or traveling salesperson problem. It's a favorite for many of us in the audience. Okay, Dan, Dick Stearns, and Phil Lewis worked on this problem. Okay, they published a very important paper in a conference in 1974, and the journal version appeared in SciComm. So Dan, how did you come to work on the traveling salesperson problem? And for example, given the results that are very nice, did it take a long time to get the results? Okay, can you comment on that?
Well, I think one advantage of being in the industry is that you can spend most of your time for a few weeks straight working on one problem. So, maybe some hard theorems, I was able to do that. I think the reason we got into traveling salesman problems because not us, but people in our group were consulting with GE's appliance business. I was talking to someone there and doing that consulting, and actually Jerry White, and he said he knew about this problem. He was addressing this problem in the factory, appliance factories. The factory would get a list of models and colors and things to manufacture during the week, like 300 Model Zs and avocado brie and so on. And they had to decide the order in which to make these. So the input was this list of things for the week. And it turns out that the way they were doing it was they had a matrix, which if you do Model A immediately after B, there's the cost of making B immediately after A, which had to do with the common parts which had to be taken in and out of the assembly lines. And they sort of complained that even though they had this matrix, the data wasn't quite right because there was some sort of things wrong with it. For instance, the cost from A to B plus the cost from B to C might be less than cost of A to C. So they thought that was defects in their data. And they imposed as traveling salesmen. They had an algorithm which was basically do something, then do the cheapest thing next, then do the cheapest thing next. And they posed it that way. But we realized it was really the traveling salesman problem. And we also realized that if the data wasn't so good, had these defects and flaws, then maybe you didn't have to solve it optimally. Maybe it'd be good enough to, and particularly if you're using this heuristic anyway, it'd be good enough to come up with a good solution efficiently. Then we met other people with same problem. There was a guy who was basically in the business of punching holes in sheets of metal, and he had to decide the order to move the machine tool from spot to spot, and he had his own heuristic. And then there was someone else who was doing sort of wire things, sculptures, drawing wires from spot to spot. He had to decide, and then he had his own algorithm. And there was someone else doing things in electronic circuits, chips, where it was going from spot to spot, making a mess. So, we encountered all these examples. Everyone we knew was doing it with some heuristic or another. Everyone had their own heuristic, and we wondering, could you say anything anything specific about how these heuristics compare? We tried simulating them in software to see that, but as theoreticians, we also wanted to see how these algorithms compared theoretically.
Great. This is one of my favorite papers I read. This is a graduate student, so I wanted to ask Dan that. Dan, Srijit Chakravarti, who's the first PhD graduate of SUNY Albany, Dan was on his thesis committee. He wants to ask a question. Okay. Sure. Srijit, please go ahead.
Hi, can you guys hear me?
Yes, hi, Srijit.
Hi, Dan. Actually, hi, Dan, Dick, and Ravi. I mean, it is great to have all my three teachers there. And, it has been, all the training and the discussions we had has had such a strong impact on my career. I cannot overestimate it. So thank you all. This is a great opportunity. And of course, I see many of my academic siblings also on the thing. It is great to connect with all of you. Maybe, I can give you many anecdotes, memorable anecdotes, starting from my PhD qualifying exam discussions with Dan to, many other discussions we had. Maybe the one that I probably even comment to my kids still today was that we were working on a problem on binary decision diagram. I forgot, it was like, I think it was an ordered binary decision diagram. And we were struggling with the proof. I think we wanted to show it could not exceed a certain depth. I don't remember the problem exactly. All that I know is that we had struggled with it for a couple of weeks. Then Dan fell ill. He went to the hospital, and he then came back after a week. And the first time he meets me in the corridor, he said, "Srijit, I've solved your problem." Okay, so you're sitting in the hospital bed and solving problems. So, and of course, I can tell you many more other things. The question I had for you, Dan, and this is probably even Dick can comment on it in his time, is that, over the years, if you look at the way the R&D labs across the United States has crumbled, you start with a G in R&D, but one can make a similar comments about Xerox PARC, TJ Watson, Bell Labs. This has completely decimated, right? And the United States has pretty much lost the lead in research. So I just want to know, your thoughts on it. Was, how did it happen? What do you think is the implication? So, I'll just wait for your answer on that. So.
I think it's a general problem for business. The emphasis on short-term profits, which is driving the way most businesses tend to be run, means there's a premium on immediate results and less of a premium on long-term research. And that's an issue for the country, the world to address.
On a related note, right, if you think about, you have probably guided many generations of PhD students, okay? And even in my short career compared to yours, I have seen a very definitive change in the training and attitudes of the PhD students graduating from our universities. At one point, it was real interest with a lot of passion for the problem that they solved and what they came up with. Everything else mattered little. I think that attitude has changed. I think the training that we impart to those students have changed. Is it just my observation, or do you share a similar observation on that front? So,
I think to some extent it has. I mean, as computer science has become more popular and more important, and more people have gone into it, their motivations expand to more things. One time there's many people interested in research or going for the PhD, but now people do it for a greater variety of reasons. And, that's natural that that's going to happen. It doesn't necessarily mean a loss of intellectual strength or rigor. It's a natural expansion of people's interests and inclinations.
Great. Thank you, Dan. Thanks, Ravi. That's all I had for now.
Welcome, Srijit. For those of you, Srijit works for Intel. He was at SUNY Buffalo, and then he moved from SUNY Buffalo to Intel some time ago. Right. Okay. Dan, the next question that I have for you is your work on concurrency control. Again, this has been called early influential work by Phil Bernstein in the book that he wrote with a few other people. Okay, what led you to work on that? Can you comment? Can you comment a little bit more on your work on concurrency control?
Well, it took me years to realize that databases was an important area. In the beginning, when I first heard about it, I thought it was sort of some variant of data structures. But I gradually realized that it was important. And then Dick Shuey, who was the head of our group, kept saying it was important. And then there was this, Phil Lewis really also spoke to people about this. There was, GE had this, and then Honeywell, actually came from Honeywell, this network database system that Charles Bachman had developed. And currency control was a big issue in that, but what really drove us was an application to nuclear fuel. It was GE had a factory, or factories which made nuclear fuel, and they were very concerned with not losing any data, keeping all the data correct, because if they lost track of anything, there were big penalties for them. It was very important to keep track of every single piece of nuclear fuel, where it was at every time. And actually, people in our group, particularly John Hutchison, designed a whole database system to support this nuclear fuel factory. And because correctness and accuracy was so important, we focused, Phil, Dick, and I focused on what does correctness mean, in this environment where there are multiple transactions running, and we kind of came to the conclusion that expect individual designers to do is write a program which would run correctly of run by itself. And then we were concerned with, well, how can you ensure that if everyone does that as their responsibility, the database system as a whole will run all these concurrent programs to maintain the correctness of the database. And so that was really our motivation. How can you guarantee that the data is correct despite the concurrent running of transactions? And so that's what drove us to do this. Meanwhile, GE didn't have the only system. IBM had this. Lots of systems were there. And when we first did this, we were calling this concept linearizable, that you could run transactions concurrently and the effect would be the same as some linear running. But then we saw this paper from IBM, particularly Jim Gray and their team, who were calling serializability. And we realized that was the same thing that we had been doing. So we were, we became aware of what they were doing. But again, our focus had been more not so much on as ensuring correctness.
So just to let you know, I work on Spanner, which is actually claims to be a linearizable database. It's a Google database, which is a distributed database and yet claims to be linearizable. So like eventually research ideas become reality.
Yes, well, right. Well, linearizability and serializability are the same thing. You know,
yes, and the thing is, most existing databases, like maybe 10 years ago, they just had serializability as a checklist item that they had it because they were required to have it, but nobody ever used it. But going forward, there's more of a serializability, linearizability are becoming important requirements which people are actually using.
Right.
And at the same time, it's performant.
Right. Actually, we constructed examples of if you didn't have strong locking, you could get non-serializable transactions. And we constructed, Phil Lewis went around to some businesses, people with applications to banking and financial things, and showed that these examples where if you could lose track of things and have bad data if things were run in the more permissive way. But we couldn't force anyone to run things the way we recommended. It was up to every application, every user group to decide, what to do.
I think in all these cases, if there's actually a a business requirement for this, it will actually become important.
Thanks, Venki. Dan, one of your PhD students, Sandeep Shukla, wants to make a comment. So Sandeep, please go ahead. So Sandeep, can you hear me?
Hear you.
Oh, great. Sandeep.
Yeah, sorry about that. I'm really, really happy to see Dan and Dick and Ravi and Madhav and everybody else. And I'm also very happy to see that through this pandemic and everything, everybody is doing well and healthy, which is quite a bit of concern everywhere, especially in the US right now. Having been trained by Dan was an amazing experience, and I keep telling my students about that experience of how Dan used to abstract out the formalized form of the core of the problem, and he used to come up with solutions. This is amazing. And what is amazing about today, I'm finding, is that how well Dan remembers all this research that he did so many years ago. That's amazing memory and amazing, reflection on all the techniques and counterexamples and things like that, which is, it keeps amazing us. I don't have any specific question, but I'm really happy to see them. And I hope that they stay as well and as active for a long time to come. And we can hear them again in another occasion.
Thank you, Sandeep.
Thank you, Sandeep.
Dan, in the interest of time, let me move on to the next part. This is the part of when you were at SUNY Albany. Okay, again, I've known Dan when I joined Albany back in 1984. Okay, Dan was there. So Dan, briefly, what prompted you to join Albany? Just can you comment on who were the faculty at the time when you joined SUNY Albany?
Well, I think I wanted to go to university at some point. I think one of the swings with the GE was kind of more applied. They're out of the computer business, and I wanted to go to university, and Albany had this new emerging PhD program, and Dean Arden was chaired. Samuel Monaco was there, and actually there were younger research. There was Yuri Breitbart there, and George Lewis, and so I went in. And Dick joined a year later. Harry Hunt joined shortly thereafter, rather fairly soon. So it had a good core group in theory and algorithms.
Victor Pan also joined.
Victor Pan, right? Victor Pan joined, right? Yes.
Right. Okay.
I never really worked with Victor. I mean, you know, he was had such command of the things he did that I never really worked with him.
That's right. What I remember hearing is that you know, people know about Strasson's algorithm for matrix multiplication. Okay, Victor Pan was trying to improve that by considering larger and larger matrices.
Right.
So typically, I think you know, you can multiply 2 by 2 matrices and using 7 multiplications to the 8. Okay, I think Victor Pan was trying to work with matrices of size 100 by 100 or something,
right,
and try to improve. Right, and he did. He succeeded in doing that. Okay.
Yes, when he presented that, it seemed so. I mean, I couldn't understand it. It was so complicated, but he had it all figured out in his head how to multiply 100 by 100 matrices and save one operation. You know, and so he, you know, that seemed you really had to be deep into that,
right,
figuring out how to do it.
That's right. Okay. Dan, the next question about your work in Albany, okay, is your work with Harry Hunt. Okay, you studied a number of problems, number of decision problems with various forms of grammars. Can you please comment on that work?
Well, again, Harry had we worked on several different areas. We worked on grammars. We worked on sort of on algebraic problems, Peter Bloniar's, you know. One work was analyzing grammars or analyzing relations, like given two things, are they same, describe the same language, given two formulas over some algebraic structure with lattices or rings or fields, are they equivalent? Is there a normal form? And we try to look at that systematically in terms of the basic algebraic properties of that structure, rings, lattices, whatever. We did a lot of things with program schemes, analyzing problems by program schemes. We did it for other problems. And again, Harry had a perspective, which I really liked, was that instead of trying to solve each problem individually, we tried to find some common structural properties which let you obtain a general result that all problems with certain aspects and certain properties will all be hard for the same reason, or will be easy for the same reason. So that was an orientation that we had, which we applied to different application areas. We even did things in database in sort of kind of locking predicates and conjunctive queries, so that perspective to analyzing those kinds of things.
Harry had this concept of extend and strongly generalize, and I like, even in real life, I encounter this and I say, this idea can be extended and strongly generalized, and every time I do that, I think of Harry.
That's right. That's right. Okay. Great. Dan, let me see. Yeah, let me move on to the work that you did with Parvati, Parvati's PhD thesis. That was on deferred updates, so-called deferred updates in distributed databases. Okay, again, that's a very interesting piece of work. I had an opportunity to participate in it. Okay, can you please comment on that, Dan?
Well, again, there were database systems, distributed systems in which, each unit of data was located at the primary site and had copies elsewhere, and transactions ran one, up using the copies that they were reading there and updating their main copy, and then the copies were sent to the other replicas. And the issue there we had was when, under that discipline, when is it serializable? And they tackle the problem of deciding which which particular location of the primary copies and the replicas would guarantee serializability, and also if there was a choice as to which to make the primary copy, how can you design those decisions so as to guarantee serializability? So again, just motivated by corrected serializability for this kind of distributed system.
Okay.
So Ravi, can I say something here?
Sure.
Yeah. So Dan, I think that before we started to work on the primary copy work, we were also doing the primary backup work. So that had some influence on the work that we did together on primary copy work. And the solution that we had was so simple that I remember talking to Ravi one night saying, this is so simple. Why didn't somebody think of it before? Do you think, do you think it wasn't published before? I was so naive in some sense, but we had such elegant solution to that work. And as Venki was saying before, serializability fell out of fashion, and then it is now coming back into fashion in the industry. And in this context, and I had a question in terms of the industry influence on the field of databases and how, I think one way we benefited is that we could see our work be integrated into some real practical work system, but at the same time, the theoretical work was also, or research was also influenced by making it practical, in some sense, even though it doesn't need that angle. And I just wanted to know from you what your thought was about that.
Thank you. I think it's sort of two goals. One is to be general and abstract,
nice,
have wider applicability, but also if there is a potential application, particularly if it's important, not every application is important, but particularly it's important, then it's very desirable to sort of make contributions which impact that. So those are two thrusts, I would say. You have to balance those and know when to just go all out for abstraction and theoretical results, and when to go all out, sometimes go all out for the application, practical applications.
Great. What I remember about that work is that the condition, as Parvati said, turned out to be extremely simple. You had to construct a certain graph for the way the copies were organized. As long as the graph was strongly acyclic, okay, the transactions were serializable. Otherwise, they were not. Okay, that kind of a simple characterization I did not expect. Yes, but okay, that was a very pleasant surprise for me at that time. So Dan, the last part we'll ask you in the interest of time. Okay, you were the associate editor and then editor-in-chief of JCM when you were at Albany. Can you comment on that experience?
Well, that was a crazy experience because the editor-in-chief basically did all the communications with the authors. The authors would submit a paper either to the editor-in-chief or to the area. And the summary editors would deal with the referees and referee reports, write a recommendation. With all the other sort of ultimate decisions, or the communications with the authors was done by the editor-in-chief. So there's a huge volume of sort of transactions in all of this. And, just part which was a large part which was also dealing with the area editors who were varied in how diligent they were. It was very hard to get people to referee things expeditiously. So there were these delays which were very hard to deal with. Also, in some cases we developed new areas, expanded the editorial board to accommodate new areas which seemed to have a lot of work going on and sort of needed more specialized editors. So for instance, we had an area for logic and computer science, but all this work coming out, but it hadn't been really consider sub-area of computer science per se, and also sort of deductive systems and questionable reasoning, and even the algorithms created a new area of sort of geometric computational geometry, because there were all this very good work going on, and it seemed to me a good idea to have a special editor for that. So, you know, things like that, adapting to changes in focus is important.
Thanks, Dan. You'll be happy to hear that Professor Mike Fisher at Yale, okay, who was the editor-in-chief before you, okay, is on this conversation. Thank you. Okay, so at this point, what I'd like to do is to hand over to Anil, okay, for parts 4 and 5 of this conversation. Okay, Anil.
Hi, can you hear me?
Yes, hi.
Yeah, so I'd like to maybe just start with saying a personal note. So I've been incredibly fortunate in having this opportunity to work with Dan during his time at BI, thanks to Madhav and Ravi. I've learned so much. I've always been amazed by the amazing beauty and succinctness of algorithms and analysis and the papers that I worked with him. One particular example, I want to just briefly mention, is this paper on Bayesian inference in the uncertainty in AI conference that I had this opportunity to participate along with Dan. I was just amazed. It just seemed like magic how Dan came up with the algorithm and the analysis. And so thank you, Dan, and I look forward to many more years of learning from you.
Thank you. It's a pleasure working with you, and I'm continuing to work with you.
Thank you. So I'd like to switch the discussion to your work in BI earlier at VT and now at UVA. So one line of work which you've been pushing is on the computational problems for discrete dynamical systems, which now has taken a life of its own in a big way. Can you say a little bit about that work, like how it came about and
well, I mean, the synchronous dynamical systems have been doing dynamical systems for decades, basically. I mean, you know, basically the guy, you know, the Biocomplexity Institute folks, even back in Los Alamos, were working on variants of that. And that seems like a really, you know, fundamental model in computational science that, and sort of motivated by that, you know, what kind of problems were of interest and sort of what, you know, what was important in that.
Yeah, we've really benefited from all the foundations you helped develop, and like that's we start almost every proposal like invoking some of those papers and that framework. So it's been really influential for us. So maybe one specific, more technical question, like I want to just bring up is your work on nested canalizing Boolean functions for analyzing biological systems. Can you briefly talk about that? It seems really beautiful work.
Well, there's somehow the people in biological systems realized that there was a special class of Boolean functions with applications to biological phenomenon. You know, whether it's each variable was a gene or protein, whatever. I never really understood the application, you know, the biology part of it. But there's been a lot of this work on this class of Boolean functions which could describe this kind of biological phenomenon. And they were analyzing and representing Boolean functions. And to us, you included, it raises a natural question of, this is a kind of representation of Boolean functions, just like grammar is a representation of the languages, and formula is a representation of algebraic things. You want to process these. So, in particular, one or two of these things equivalent with expressive power are the various restrictions. Can you reduce it? Can you test for equivalence and implication? And also for dynamical systems whose each of whose components are described with Boolean function like this, how can you analyze, can this restriction to each component operating as an NCF affect the analysis of that dynamical system? So we were motivated by this. Again, the class of Boolean functions were developed by biological inspired people, but the analysis of these things with mathematical and theoretical objects is what we focused on.
Yeah. Thanks, very nice. So are there other research topics that you would like to that you're interested in developing in the near future?
Well, I think dynamical systems still is going to continue. I think it's so fundamental that it's going to continue to develop by various communities. There's a whole group doing Boolean networks, biologically inspired dynamic systems happen to be directed, RAS, and they've been doing very similar things, but perhaps with different terminology and notation. I think if some model is important, that's going to happen. Different groups are going to use their own terminology to describe it. And we've recently been working on the acyclic Boolean networks or acyclic systems to analyze those. So I think that's going to continue. The epidemiological models like SIR, we've actually been working on theoretical analysis of those for a while. There's other problems, maybe multiple contagions in the network, or maybe the effect of countermeasures on the network. So those are other problems well worth investigating.
Sure, thanks. Very nice. So maybe I'll open up the floor to everyone if there are questions related to this part of the discussion.
And just one quick comment. It's about 2:15.
Okay. Yeah.
So at least we can continue a little bit after 2:30, but we should just keep that in mind. I just want to let you know.
Okay. Thanks. Yeah. Yeah. Maybe like one quick question if there is.
Okay. I could make a brief remark about Boolean functions that they, as others have said, they found many applications, and I think in terms at an abstract level, we want to model computations, and of course Turing machines give the I guess a kind of dynamical system approach where it evolves over time. And a Boolean function is static, and it gives different complexity measures, but it also gives a combinatorial way of analyzing computation that in some cases is powerful. And I've been working in cryptography for a while, and the Boolean function model has been used for analyzing privacy preserving computations. So I just think that's the idea of transforming a dynamical system into a static one can sometimes give helpful insights. not always.
Yeah.
Professor Fisher, we really are so delighted that you can join us. Thank you very much for joining us on this special occasion.
Okay, well, I apologize for being an hour late when I got here, but I at least heard a little bit of the discussion now.
Yeah, that's wonderful.
Yeah. So maybe in interest of time, I'll move to the last part, and then we can have some discussion over any of these parts depending on how much time we have. Dan, I'd like to start with asking about the history of Stock and Fox, the premier conferences in theoretical computer science. What was the culture like in the earlier times, and do you like how they become now? Do you feel they're too technical, or what your impressions are from that?
Well, I mean, history, I think that they, the original conference was something like logical design switching theory.
Oh.
And then it changed, kept changing, it's changed its name a few times. It came automata switching theory, and then foundation of computer science. It kept generalizing the name as the interests of the members changed, and it became a model of what a computer science conference should be. I think it was a pioneering model. I think people like Uris and Ray Miller and Dick and Phil and Seymour Ginsburg had a strong influence in what kind of conference that is. And at the time, the engineering conferences and the computer science conferences tend to be very large conferences with lots of papers, parallel sessions. Many of the papers, probably most of the papers are kind of routine. And the model that this conference created was of a small conference with maybe like 30 papers or so, and very high quality, and maybe more specialized, in particularly theory. So it created a model which propagated to other areas of computer science. And it sort of made computer science different than other scientific disciplines, because it contributed to the idea that computer science conference publications are really important.
Mm-hmm.
Maybe more important than journal publications. And folks in other disciplines, have a very hard time accepting that. And the nature of these small conferences just makes the view of evaluating people different because of how important conferences are. So, and that splintered at some point more and more. I think Mike was involved in creating the, I think I was on early program committees. I think one was Mike on principal programming languages, the first one. That was a split off course. Thought was such an important area which needed its own community and program committee. And there was a PODS, which I was a principles of database systems, which I was on there's program committee, because there's also a feeling that programming, that database systems deserved, or not deserves is the right word, would benefit from its own theoretically focused conference. And so an conference that's hard. At one time, the theoreticians could attend 1 or 2 conferences a year and know almost everything that was going on in theoretical computer science. That inevitably has gone by the wayside. People have to pick and choose at this point.
Yeah. So I had other questions, but maybe I'm going to skip in interest of time. So one which a lot of people on this call would value is what would be your advice to young computer scientists on I guess it's an open-ended thing, about how to choose problems to work on, how to know how long to persist, and and any other advice you can think of.
Oh, I think different people have different styles. I mean, there's some people who spend 10 years addressing the same problem, and usually they eventually crack it. So in some sense, it's what you're comfortable with. In general, it's good to, if you can tackle a problem with applications, that's good. You know, particularly if it can impact applications, that's really good. If you can tackle a problem which seems fundamental importance, that's really good. You know, how long you persist is, I think it's good also to get some results at the beginning, even if they're small, just get started with some results and then tackle more difficult problems. Talking to people in other areas is really good because you can find out about other problems from the people you talk to. Just like talking to Gary from the business school, that we discovered those problems. You know, talking to other people, even if they don't speak, generally people in other disciplines, particularly engineering, tend to be far more informal. So you have to talk to them, you know, to explore what the right model is and ask them questions, you know, if you do this, does it make sense or not? So I think it's good to have people that you can talk to from other disciplines that you can somehow or another manage to communicate with.
Thank you. I'm sure our junior colleagues on the call would find this really valuable as they as they navigate computer science. So maybe a follow-up on that, can you, so this is like a prediction type question. Can you say a little bit about what do you think of CS maybe in the next 15 years? We've seen so many cycles in terms of the areas which have come and gone. And are you surprised computer science has become so influential?
Well, I think areas will keep coming and going. That's inevitable. You know, new areas will emerge, you know, particularly for theoreticians, but new areas will emerge. If they first emerge, a lot of people jump into them, and first they do the low-hanging fruit, and then they focus on them more and start solving more deeper problems. And at some point, those areas might get mined out, or if they're fundamental, then they'll continue. And should always be, you know, kind of always be prepared to go into something new that you realize is important. And again, new applications will keep coming up. I mean, I think computer science is now so fundamental to almost everything that goes on in society that that there can always be, at least in the definite future, always be important to be doing computer science related research.
Oh, yes, yeah. Did you have an inkling of how computer science would explode when you were starting? So you said you were interested, you got into it because you were interested. Did you think it was going to become so central?
I may have thought that, but I certainly wasn't saying it. I mean, you know, it seemed really important to lots of areas. I think you appreciate how much people from these areas would actually be doing, the extent to which they would be actually doing computer science. They knew all these areas would be doing programming. At some point, they realized a good proportion of the electrical engineers and physicists were actually doing programming in one sense or another, building systems, doing programs, working in computer science. And so I kind of had the feeling that that would continue and even expand.
So, sorry to interrupt, Dan. On a related note, what are some of the surprising developments in computer science that happened in today that 20 years ago you thought would probably not have happened? What are some of the surprises that computer science has sprung up today that you thought?
Well, I guess one thing that surprised me is how successful machine learning and deep learning is. I mean, I thought that was important, but to just be one of several techniques and house applications, but the widespread use by so many different communities sort of was something I didn't really expect.
Anil, if it's okay with you, we can maybe open the floor for others.
Maybe I'll just ask one last question.
Yeah, please.
So yeah, Dan, I think through this conversation and we've learned a lot about your interest in computer science and the sciences. Just curious what your interests beyond computer science are.
Well, I think I'm interested in bridge. When we came down to Florida, I started playing a lot of bridge. I'm interested in that. I'm kind of interested in happening in the world, politics and news and things like that. So interested in that. I'm interested in movies and theater, things like that.
Nice. Yeah, thanks. So maybe we can open up.
Right. Anil, I just want to take just 30 seconds to say thank you to Professor Fisher. Errol Lloyd is here, and it's good to see him. Meiru Sofa is here, and it's good to see her. So maybe Dan's lecture has brought all these folks together who are colleagues back at Pittsburgh. So I think there's a very good side effect that we have felt today. I have not seen Professor Fisher for a long time. Dan, maybe this is a great lecture in that sense. And also all your students. I mean, we have Jonathan Stillman and Srijit and Phil and all the way to the more recent students. So in that sense, this has been a wonderful meeting. I should, if it's okay, Anil and Ravi, let's open the floor, and others who have not had a chance to ask questions or make comments. This might be a good time, and we can take next 15 minutes to do that. So if it's okay with everyone, let's try to do that. So please go ahead and ask your questions. Anybody who has a question or thoughts.
So, Dan, in part one, I must say I love the fact that your nickname in the early days was Mr. Counterexample. And I'm wondering if there's any particular problems or problem at that time that you remember or that particularly motivated you in terms of your problem-solving career. I thought that was great.
I don't remember at this point. I think, particularly switching theory and, had all these discrete math things. And it is opportunity to construct counterexamples to conjectures, logic design. I think there are other things, computer networks, even not computer networks, circuits, engineering type things. There were things which was essentially graph theory, graph analysis, things like that. There were conjectures possibly about graphs, which it was fun to try to see if they were true or not. A lot of problems tackle was, on one hand, try to prove a theorem that this is the way it is, but at the same time also work in constructing a counterexample to show, no, that's not the way this is. So it's a two-pronged attack on problems. I don't really remember the specifics at this point.
Okay, yeah, makes sense.
Dan, I'll just ask one quick question. The reason is that you are here, Dick is here, and I'm going to ask the same question to Dick tomorrow as well, and Mike Fisher is here, because I think we cannot have a meeting of such theoreticians without asking the PNP question and take 3 different views on it. So I let you go first. I'm sure Dick will have a view tomorrow. You can have a view today as well. And Mike, you should have a thought as well, because I think it's such a central question that has brought our field together. And as Kunut said at the ACM meeting, I think mathematicians did not think much of computer scientists till this question got formalized, and it has reached a stage where mathematicians are struggling with it as much as we all are. So it has given our field a certain amount of credibility in the mathematical world, I guess. So Dan, do you want to say a little bit on what you think about that question? Of course, Dick will say a lot tomorrow.
Well, I have no insight. I think they're different, but I have no no insight in how to go about showing that. If I had, I would have tackled it. I kind of remember in the 70s when this problem posed. I remember talking with some OR people, and I think they had, even though they had the problems and were using programs to solve them, people I spoke to didn't have any appreciation of computational complexity issues. Talking about traveling skeleton problems, their attitude was reduce everything to linear programming and basically use a general purpose program to solve it. And I was constructing counter examples showing that the size of the linear program expression of this combinatorial problem would be exponential, and sort of that concept couldn't communicate. I couldn't communicate with them, and they couldn't communicate with me. And I think now it's changed. Now the people in the application areas really understand that complexity is important.
Yeah.
And efficiency is important.
Dan, sorry, let me just make one remark and also ask a question of Dan. The first remark is that I think we were talking about counterexamples. I remember attending a seminar, I think I don't remember the name of the faculty member. He was giving a seminar in the department, something about distributed something. Okay, he was presenting it. I guess they had already written the paper. He was talking about it, and during the lecture, Dan found a counterexample to the algorithm. Okay, I remember this. Okay, the second is a question to Dan. Okay, during your JCM editorship, did you get a number of submissions claiming P to be equal to NP or not equal to NP? Do you remember getting many submissions or none at all? Or?
Yes, there was a few yes, I mean, not every few months, maybe one would come in, and as the editor versus the editor and then the chief, I generally handled those myself. Generally, there was a flaw. I could find the flaw to someone by the perspective from a certain area, and there were flaws in them. And the question, I don't remember if I ever sent it to an area rather. My first inclination was to read enough to find the flaw, and most of them had something naive about them that I could reject it out of hand. But I don't remember if I sent any to the area. And there's some, I don't know if Mike remembers when he was editor-in-chief, how many he got and what he did with them.
Mike, you want to say something about it?
Yeah, I mean, we've all gotten many solutions to P equals NP. I think it's the most solved problem that's out there.
Nicely said. Yeah, well, most solved problem. Yeah.
There were a couple comments I wanted to make to the earlier question about what did I find most surprising, and I have two quick anecdotes. So one is that I was a math undergrad at Michigan. That was in the early '60s, and there were a certain number of electives required. So I thought, gee, number theory sounds cool. I had no idea what it was, and I went to the first class. It was Professor Levac was teaching it, and he said, the great thing about number theory is it's the one area of mathematics that has no applications. And of course, today it's had a tremendous number. And the other thing that I think really surprised me was that in those early days, when I was a graduate student at Harvard, people were exploring applications such as spell checkers. And I thought then that, and also information retrieval. And I thought, well, maybe someday somebody will build a spell checker, but the first thing you have to do, and of course this is not anticipating some of the newer algorithms. First thing you have to do is to input a dictionary, and who is going to be spending the hundreds of hours typing in all the words of a dictionary? I could not imagine the scale that computing has grown to, the fact that yes, there are millions of people out there doing these tasks, and while one individual is limited in what they can do, collectively, people have done really unbelievable things. And I just could not imagine that actually happening.
Very cool. Any other comments from the group?
Madhav, I just wanted to make one very, it may sound humorous, but it is a very deep comment. I think this was Network Design Day, I think in 98 sometime. I think you were there, Ravi was there. Ravi put together a great day of talks. At that time, I was still naive. I was very new to Albany at that time. And I was in one of the presentations. I think Ravi gave Ravi from CMU. I think he gave a very good talk. He's a very good speaker. It was a very complex technique. I had no clue what he was trying to do, but he made it very, very presentable. I got through about 60% of his talk. After that, he lost me completely. After that, it was all equations. It was all heavy math, and it went overhead. Dan was very quiet throughout the entire talk. And at the very end, when he asked, "Do you have any questions?" About 60% of the time, I understood the question. I couldn't even ask any question because it was beyond that. It was beyond my understanding. But Dan picked the most complicated equation out of the entire talk, and he actually ripped it apart. In the sense, he was very quiet throughout the talk, and then at the very end, he was probably one of the very few people in the room who understood exactly what Ravi was trying to get at. And that kind of floored me at that time, because at that time my honest thought was, even if I had 2% of his brains, I'd be somewhere else. And that was really eye-opening. And he has, I think towards the end, I came to understand that if Dan is very silent throughout the entire talk, there are two things. One is he either completely understands what the speaker is trying to say, or he thinks the idea is extremely trivial, that he cannot answer any, he should not ask any questions. So I just wanted to share that with you.
Thanks, Ganesh. Thanks. Maybe we should give a chance to Jonathan Stillman, and I don't know whether Tom O'Connell is around, but Neil is around too. Wow, Neil, hello. So any of you want to say a few words, that would be wonderful.
Well, I had a number of things going through my head, but one of them, of course, Dan and I have very little in common with Dan and Dick, other than the fact that we were all chair at one point. And I'm just imagine, I can't remember specifically, but I know when I was chair, the comments about how the development of computer science conferences, if you're a chair and you're guiding a tenure case through, or a promotion to full even, one of the things that I would have as a standard chunk of my chair's letter was this attempt to explain to people outside the field of the importance of conference papers. And I assume, Dan, and probably you too, Dick, that you folks had the same sort of little tool that you had to use every single time, because when the case moved up and people from English or philosophy were looking at these things, they would look at all these conference publications and, 12 papers at stock, who cares? So anyway, that's a little anecdote that I remember having had to go through that process.
Thanks, Neil. Wonderful to see you. Last couple of minutes. So any thoughts from folks, especially who haven't spoken? We want to make sure that everybody gets a chance to speak and say a few words. Tom is there, Jonathan is there. If you are, please go ahead.
Hey, Madhav.
Hi.
I just want to thank you guys for putting this together. It's been great to see everybody. I haven't seen in a very, very long time. And some faces that I've never actually seen before, but have heard a lot about from the previous Albany groups. So it's been great, Dan. Your insights into everything have been. I've been taking notes here. I'm teaching theory of computation next semester, and I'm taking notes here for my students to give some stories. So thank you very much.
Thanks, Tom. Wonderful. Jonathan, do you want to say anything? We can't hear you.
John,
okay. Yes. Yeah, I had to find how to turn my mute off. Yeah, I'm certainly glad that you guys have organized this. It was great to kind of walk down the memory lane with not only Dan but every number of other colleagues and fellow students. Some I had only brief encounters with. Others we spent a lot of time together. Some of you may know that Dan, after he left GE R&D and went to Albany, he also and sometimes for me came back to the research center as an advisor and counsel, and even then I in particular valued his voice for his ability to balance carefully theory and practice. And for me, that's probably, Dan, one of the biggest things I took away from my many hours with you is that while I love computer science, I really wanted my work to make a practical difference. And you were the person who showed me how to do that without being sloppy in practice and not being too erudite in theory. And that I took with me, even though I moved away in some respects from research after a few years at GE and left GE to go on to become a venture investor and start a couple of companies and so on. I always kept that kind of perspective with me, and it helped me an awful lot. So I didn't that to me that you either teased out the theoretically interesting thing, the problem to be solved there in theory, or you from a practical perspective, or conversely, and seemingly with just as much ease, took a theoretical question and found something that it would relate to in practice that was pretty interesting too. So thanks for that, and I've as I say, I've benefited a lot from that, from your perspective on that.
Thank you very much, John. If it's okay with everyone, would like to let's close the session. Chris Barrett is online. I first want to remind everyone that tomorrow at 1 o'clock we'll have Dick speak, and we'll have a discussion with Dick, Mary Lou Sofa, myself, and Ravi will moderate that session, and I hope everybody can join. Mike, if you can join, that would be wonderful, of course. But Chris, if you have you have the floor for the last set of comments, and then we can close.
Well, hold on a second. Well, I'm not going to, my camera, I've got a bandwidth problem. I'm going to leave my camera off. I just think this has been super interesting, and I would love to hear, I have to say that I'm teased with needing to hear a technical talk. So yeah, that was a wonderful thing. I would really like to, I hope in the discussions that we have as this going forward with everybody on the side, that we have the opportunity to really get to know these guys again. I just want to thank everybody. I don't know what else to say. It's just been a really, really inspiring and wonderful afternoon.
Thanks, Chris. Just to remind everyone again, tomorrow it's Dick's turn, and then the day after, Josephine Lamp Andrew, and Arash are going to moderate a session that is largely geared towards young faculty members and students. Of course, all of us will, I'm going to join for sure, and I hope you all can join, but the questions are going to be much more around careers and, general broad issues. And maybe that's a chance also for them to discuss and even argue about the point in different ways. But thank you very much once again. It's a pleasure that we could have this, and I hope our students in particular liked this, and also my fellow Albany mates. It's a pleasure to have you folks join us today. All of you. I've not seen you for many years now, so I would not have probably recognized some of you on the street. So this is good to know. Thank you very much again. I hope we can see each other again tomorrow at 1 o'clock. Thanks, Anil, Ravi, Grace, and others for organizing this. Pleasure to do this. So with that, we'll bring this to an official close. Dan, thank you very much again.
Thank you very much.
Grateful, that you could do this. Take care.
Great.
Thank you. Yeah, bye.
Bye, everybody.
Bye.
Thank you. Thanks, Madhav.
Yeah, bye.
Bye. Bye. Thank you very much. Bye.
Bye.